Good afternoon, everyone. Today I'm going to talk about our multi-scale application software framework and some experiences developed on uh, the system called Islamabad. It's a ARM Thunder X2 based machine. Just before giving my talk, I'd like to tell you where I'm coming from. So this is the whole UK map, and where we are, I am based is in Daresbury. So our UK actually divided whole research council into seven big research councils. What our council called Science and Technology Facility Council, and we have about like actually seven sites, and we have quite a few big national labs. Our national labs called Daresbury Laboratory. Hartree Center is one of there is only two national HPC center in UK. We are one of high performance computing center, particularly targeted to industries. So today there is my talk composed of three sections. So first is just introduction of multi-scale simulation framework, and then our early porting experience on Islamabad, and then discussion of some potential future work. So this graph is just roughly give you the diagram of the scale hierarchies, how our software is actually working on. So this is give you both spatial scales and also time scales as well. So in between atoms, like from 1 to several thousand, we're basically working on all the quantum mechanics field. And those using familiar with first principles, to working on particularly fundamental properties of materials, particularly like alloy, etc. And for atomic processing, like when you study about the material deformation and particularly defects formation, and also and its evolution, what made is one of the molecular dynamics we want to deal with. Our molecular dynamics called dual poly, and in further upscales like meso scale simulation, which what you can work on is like a semi-related dynamic process, like you can do phase transformation. You can also simulate various thermodynamics field. So this what we have another software package what we call Meso. And then in the next into the continuum field, we have quite a few CFD software package. Where I particularly working on is a particle-based method called SPH. Today, and also we have a finite element methods. So this kind of in the continuum field, you can also simulate in the mechanic process like welding. So particularly this gives you the whole structure of the digital manufacturing, what you can do in terms of improving material performance. So this and so next slide is basically based on the so I would say more than 10 years history. Our software packages that particularly developed for the material simulations. So majority software engine is DL Poly and DL Meso, which is MD and mesoscale simulation, and also involves several package using the coloring methods. And although we also have a bridge between your quantum mechanics field, and actually there are also two software package in that scale, but I think the main developers they actually moved to the different university now, so they are not in our lab anymore. And Sorry. And the main purpose is trying to introduce you is there is ongoing effort at actually trying to build a digital training environment. And in order to have this effective digital training environment, we need actually quite a few things. First thing is actually for individual skill, you need better understanding what's the physics, and you need to actually simulate the right physics. So this is the key things you need to practice. This is based on the more than 10 years experiences in this field, the research field. And this ongoing effort and also trying to combine with machine learning. So the whole process can be automatic and also give more in-depth understanding in terms of huge data generated from the simulation. For the dual poly, I can roughly give you so as a major software, we have a reasonable size user community across the world. Particularly, we have like more than nearly 10% from China and also more than 10% about from USA. Majority from EU and the UK. But recently, we are actually thinking of code renovation for the dual poly, and you can see from this now the email changes seems going down, but I think this is just because of process of we are actually for the polys are in the called refactoring stage at the moment. So just roughly doing what DL poly MD can do. So you can do like protein solvent and binding. You can also do DNA dynamics analysis. You can also membrane process and also drug this new drug discovery research. And particularly when doing manufacturing process, you all need to see how the damage and recovery being processed. Another thing is dynamic processing mental. So this is all key tools can help you to understand the basic material properties. And for the deal Meso package with the measure scale simulation toolkit, they're actually composed by two numerical methods. One is lattice Boltzmann methods. Another thing is called dissipative particle dynamics. DPD has become more popular now. I think it's originally coming from Europe, but now it's being adopted widely and also quite efficiently as a cost scale from MD code. So, and as for Meso, we have more than 800 academic license, but we are not quite open source license. We kind of like all we are, for academic they are free, but for industrials you might need to issue a new license from from STFC. At the moment, DO Meso actually have a big project with Unilever trying to do the it's called computer aided formulation simulation. So it's being heavily developed at the moment. For the CFD package, we basically mesoscale from we see trying to bridge all the manufacturing process in terms of all the parts you need to understand, particularly like material strengths and also when you do welding, how do you make sure your parts is quality is guaranteed. So in that sense, you have to really working on the continuum field as well. So we are trying to adapt our FEM code and also SPH code to working for this purpose. Although all these packages have been also established in other fields as well, particularly like nuclear field and also in renewable energy field as well. So another thing is we actually borrowed from open source framework, open source toolkit. This is particularly good. So it's called the multi-scale universal interface. It's originally developed from Brown University, and we're working with them actually trying to extend their functionality. What they actually do is trying to bridge as an interface to coupling between these different scales. to do that, you need to actually to make sure if you want to have a general and non-expert library which can help you to do coupling. This is exactly tools what you want to look at. So it defines a general data points as a to trying to abstract how different numerical methods. For example, here you have finite difference, you have finite element, you have a molecular MD methods. What you could do is if you in traditionally if you have a finite difference, you have to define all your grid points like this way. And in finite element, you can define your points, which unstructured points, which more how if you want to describe in complex shape. Then what they actually trying to look at is if you trying to find all the points, so you can define the points in this way. What nice point is you can define from software development point of view, and for the data point of view, you actually have all common points is you can define all the field data along the points. So with this, you need again to trying to have where's my point? Can't find it anymore. It seems all power. So you need to have a define a basic tool to actually to do the data exchange. When you do the data exchange, there's two things you need to keep. First thing is um, how do you actually push the data into this middle interface so that you do exchange. Second thing is how do you grab the data into the different model. So to push into the common interface where you can, so this is called push, what defined called the push action. You can using data points, and so you can push everything in this common data points interface area. And second thing is when you do a fetch for different model, this will involve more expertise because using different numerical methods that they can copy the different points. Then this is where the issue coming from is how do you actually to get the value, because in the finite difference point, your point may not exactly match when you get from this common interface. Therefore, you have kind of like using neighbor schemes, or you can using somehow weighted interpolation schemes trying to interpolate the points where you actually need it. So these provide a user interface for you to do the interpolation or special weighted function you want to use. They also have some default few function you can actually use, so you don't have to actually define your own interpolation operator for yourself. So with these two and with optimized MPI communication functions, you actually can easily for you to use this interface to simulate these multi-scales concurrently. So this is basically provide you a concurrent coupling tools for you. Yeah. So so I basically give you a scale from MD, from a Meso scale, from the continuum scale, and also tools how to coupling them together. And then the next thing is when we working actually for the performance-wise, what we want to do. So here is a majority is basically how do I abstract all these mainly related with performance critical functions, what you can to optimize, particularly towards different computing architectures. So for example, you have a bottom layer, you have different programming language, programming library you need to use. And in the middle layer, you have basically you do parallel, you need the domain decomposition, you need, if you're solving incompressible problem, you have to have sparse linear solver. If you doing mesh based or particle based, you need to consider how to have efficient ordering kernel. And in the up level, you define the different math operators, which is more related with you have a math intrinsics. Can you have utilize all those math intrinsics from different vendor specific libraries? And then if you have mesh-based, you need pre-processing, then all these tools will become available to you, but they are may not performance optimized. But what you have to do is you have to, for us is if we want something like a efficient uh, uh, framework, you have to working on those kernels, trying to optimize it. So this is just part of work we want to do in our group. Yeah, so this is talk about just the introduction about our framework, and then the second thing is just give some experiences for porting the whole software framework on ARM platform. So before doing that, I'll give you some platform introduction. So for Isambard system, this is our another research council is basically trying to set up the whole what we call regional HPC center. The regional HPC center, there's four system which we call tier 2 system. So this is one system which based at the University of Bristol. The PI is a Professor Simon McIntosh Smith. I think probably in the group you have seen, you probably already know him already well. So the whole system have ARM8 cores about 10,000, more than 10,000, and use Cree XC50. It's high-speed iron interconnect. It's also comes with Cree whole HPC build environment across ARM as well. The major compute node called KVM Thunder X2. So just to give you what I think in previous talks also you notice about Stream and Clover, Leaf, and T-Leaf. So this is quite few software, many apps is both covered like mesh-based Monte Carlo and also neutron transport, these many apps. So I got this slides from Professor Simon, and this is basically give you a story what's so before I give you the performance graph, so this is basically everything trying to normalize according to Broadwell. So this is when you compare the performance of Broadwell, so the higher is actually the better for the performance. You can see because the ARM processor have higher bandwidth, so for stream you can get better results for many apps. And also Cloudleaf, it's a stencil-based code, so with proper tuning, you can actually get better results, even better than Skylake. But few codes, if we more floating operation bounded, you kind of get well, still a reasonable performance compared with Intel-based architecture. There's another single node performance results. It's also compared with Broadwell, and this is major UK national supercomputer on the Archer. So this is the top. So actually in the top 10. So this is most used top 10 codes in the UK National Supercomputing Center. Nice story coming here is for all like a particle-based code, they're not performing that well as we want, but they are reasonable. For like OpenFOAM, because it's more memory bounded code, so if you compare with like Broadwell and Skylake, they're actually much better because of this memory, high memory bandwidth. So that's another thing you look at is when you actually trying to compare, you need to really consider how your performance character of your code. Here I get this early performance code because I only get one node access, so I only have one node results. So this dual poly is MPI OpenMP parallelized. I only pair using MPI. We don't have any issues, so I don't want to show that. It's quite scalable. For multi-threading, we recently have some new results, particularly targeted for those synchronization. So we actually get better results with newly updated multi-threading code. So this is just trying to compile if we use a different like a static, guarded, and also dynamic scheduler, what's the performance coming out from. So with using 32 threads, but using, because this machine, the whole machine being, I think it's 4 SMT. So I only use like 1 thread per core, but for 2 thread and 4 thread, they are not that as good as we want. But I think there is hardware reasons. I can't remember what exactly. So you might want to tell me. We had a good discussion. So, and for DL Meso part, scalability is very good as well for, because it's been very. This is the MPI result. So basically, it's almost linear scaling within node. And for the ISPH code, so ISPH is a particle-based methods. So, oh no, uh, particle-based methods. And the particular thing is because incompressible SPH, so you need to solve a Poisson equation. So it's related to sparse linear solver. So you can see we're actually using the PATI to do that. So it's pressure Poisson solvers you actually solved by PATI. To install a PATI normally is quite headache in every system, but we can see successfully ported everything on the ARM without too much issue. Take like as same as before. So that's one good story for ARM. Another thing is when you see all the scaling factors actually quite good. But I think it's probably more interesting to compare with other Intel based. You can see DL Poly and DL Meso, they're okay. I mean, they being pretty much optimized by Intel. But for the ISPH, because sparse linear solvers occupy quite large chunk of time, so they actually gives much good results. Yeah. So this is basically our whole experience. Is another thing I didn't mention is when we porting everything to the ARM, we didn't really spend much time to do that. So one of the key things is when you trying to port those exist like a software stack, you can easily get the recipes from this DV forum. That's one thing. So to make things smooth. Another thing is because I think they have priority to actually have a GNU working first. So anything we do, if you have a GNU compiler working for GNU compiler, so that makes things I think work in the ARM in the first. So this is I think a very good strategy. Another thing is when you do actually using ARM-based compilers, sometimes you come across issues. Sometimes I think it works as expected. So particular things is I think it's all probably, if I may talk you in the back, next slides. Another thing is a lot of these open source tools you can actually install on there. So this just helps in terms of porting exercise. For another thing, so I think more feature we want is since the first thing is ARM processor does not trap in integer divided by 0. Sometimes when we do develop, you can't just get also like result 1 divided 0 equal to 0. So this is one major thing is what we want is be hard to really debug everything. So when you're trying to want to debug the program, but you do trap for the float. So that's a good thing. Another thing is I mean, automatic for developer software, when you're trying to build systems, this all basically work. But for those old config, they're not being updated. If you're trying to use auto config, you might get some fail message. That's just because processors being. So if you use the latest config.s, config.sub, you should solve the issues. For the weekly memory model, there's some causing some issues about, especially you are using like P threads trying to develop lock-free models. You might come across issues for this. So we had some issue for this. So this needs guidelines. How do particularly how do you actually deal with these kind of issues? And I think it's a lot of our frameworks, particularly like DL Meso, we have GPU enabled. So how do we do using GPU? I think that's questions about because a driver is not available. So how do we connect it with them? So need help from vendors, need help from you guys, actually. For more math libraries, this is it's not exactly the same math libraries or other like ecosystems. Especially, I didn't find like when you do ecosystem, is particularly since when you do parallel, everything actually have domain decomposition, dynamic load balancing, but you didn't put that as a library itself. So why don't you, so I would suggest why can't we just do this? Because when you're actually looking about all your parallel profiling, you actually domain decomposition, dynamic load balancing is actually counting quite a lot of time there. So, so if you have optimized the library for this, then it will improve the whole performance as well. Another thing is sparse linear solver, particular threaded libraries, because your CPU-based architectures for multi-threaded libraries for sparse linear solvers are not many actually available. So there's need some lot efforts actually for if you want just trying to use CPU-based architectures. So this is I basically copied the slides from so everything is available and you can easily get all from ARM HPC and you can install it. One key issue is a lot of them may not be updated. So what's the strategy actually to keep it updated if there is new release? But a lot of them they may not release often, but if you release often, how do you actually keep it like updated? Because there might occasional issues. Another thing is for profiling tools. For profiling tools, at the moment, majority we are actually working on these kind of fields. So it's MPI based. How do you make sure I have a lot of balance in merit? And but for the serial code performance, there's a lot of this space. This can be explored. How do we actually explore this efficiently? Which one is actually the major effects? Another thing is even you got numbers, how do I interpret these numbers? Is also a good question. Depends on, for example, your cache miss rate. Sometimes you get 90%, sometimes you get 99%. But what that means to the users, whether it's good number or it's a bad number, depends on the applications. So how do we to actually interpret? There's a lot of things need to actually to help in this sense. So basic summaries. So there are quite early results we generate quickly in a few days with not many like scaling issues. I think to be fair, the whole software stack is quite robust and reliable and also I would think high quality as well. Just to show, I think I have this. So so the Islam system is about 10,000 cores, unsure node, but Professor, they just make the whole system work. So this is GrowMax. So you can see the scalability on this system also are quite good as well. So it's about 50% of with about, I think it's 8,000 cores. So in this, I finished my talk. If any questions, I'll be ready for your answer.
Thank you, Dr. Wu. Any questions? So you just mentioned the GPU support for this part, right? So I just want, are you just using NVIDIA CUDA or you are also using OpenCL?
We actually using both. So for DL Meso, we actually have a paper submission. So we basically optimize only using like if we have results for NVIDIA V100, we can scale well up to more than 2,000 GPU cards. So, but if you want to apply ARM, we know it's not easily to connect. You buy a card connected to the nodes because the driver is not there. Yeah. So it's not. So basically not connectable. I think there are some issues trying to
yeah, because I mentioned this because, for example, for OpenCL, potentially the open source AMD GPU driver can be used right here. Right, this can be probably a first step to have GPU support in this area before NVIDIA can provide some official ARM support.
Yeah,
right?
That's a fair.
Yeah, not so much. no OpenCL. Yeah, no
Yeah.
OpenCL in Mesa, but
Yeah.
AMD has the open source OpenCL support.
Yeah, we are
Yeah.
aware of that.
Yeah.
In fact, we have a EuroX project. We're actually using OpenCL as well. So
Okay.
yeah,
Great.
but because we could use actually NVIDIA. So,
Yeah.
yeah.
Okay.
Yeah.
Thank you.
Mhm.
So you were asking a question about, you know, how do you go about understanding which of the profile results
Yeah.
do you how do you interpret those numbers and which one do you run first?
Yeah.
So one of the things that we looked into this, and we spoke to some of the labs, and our idea, we only started this, so we haven't done a lot of in this area, is to use a higher level profiler like perf,
Yeah.
to get some numbers. We know it's not like the best number possible, but it's like kind of a ballpark. And then you do a statistical analysis, like multivariate analysis, like principal component, that to understand for each one of the benchmarks, what is the profiling numbers that affect the most when you change the architecture, or you change the memory, or you change the compiler, for instance.
Yeah.
And that will tell you for that specific application which will be the profiling item that you care the most. And then you can just look at that and accept that the rest will be more or less the same, but that will be so cache misses is important for one because the matrices don't quite align,
Yeah.
and branch misprediction is important for the other because there's a lot of if conversion that didn't work well. So that will depend on the application.
Exactly. But if you're looking at about this parameter space we can explore, it's quite a lot.
Yeah.
A lot of effort you need.
So no, so
how do you
this is
actually
why
facilitate this effort into that?
So that's what I mean. If you use a
Yeah.
multivariate analysis, you can just collect all of the data and then run the multivariate analysis
Yeah.
on it, and then you pick like
Absolutely.
the top two.
Yeah, absolutely.
And then you don't care
But
about anything else.
the key thing is, can we have these tools available for people easily to use? That's the key thing.
Yeah, you can develop it, and then we'll have available.
Thanks.
So I'd like to ask you the Fortran compiler. Fortran compiler.
Yeah.
So and especially how good is Cray compiler?
So actually, we have two codes. So DL Poly and DL Meso are actually all Fortran based. So we are changing to C++, but at the moment, I think if you say how good, I think for ARM, because they actually use PGR Flan, so they said it's 2003 ready, but it's not 2008 yet. So there's a lot of things. If you want to use 2008 feature, you have to wait, I think. That's one thing. But if you use like a Fortran 95 or 2003, I think in general, you wouldn't observe big difference.
About the quality of the code? Quality of the code generated by the Fortran compiler?
You mean comparative?
Quality.
Oh, quality. For our code, or quality for the compiler? What do you mean?
Yeah. Which compiler is the first? The code generated the compiler.
I can't really kind of answer what kind of thing. So when you talking about like a speed of generator,
yeah, speed. Yes.
I think my experience is little bit slow. Yeah, it's a bit slow.